ICND2, the second review of the material that we've covered Wednesday and Thursday, and of course we now have the today's stuff. So we talked about routing protocols, and we had two different types. We had the distance vector and the link state. Distance vector was, I guess, one of the noted things for distance vector was that it shared its entire route table on a regular basis. RIP was that protocol that we talked about. And it shared its routing database, its full database, in broadcast format every 30 seconds. Causes a lot of broadcast traffic. Distance vector, small network. And then we had the link states. The true link state protocol was OSPF, and then we had EIGRP, which is a hybrid, and it's down there a little bit later. Hybrid exhibits the traits of both a link state and a distance vector protocol. Link state, in that the updates are based on the state of the links, and that's one of those. Do we have neighbors? Are we communicating with the neighbors? And the hybrid, the characteristics of distance vector that it exhibits is that it initially shares its entire route table, and after that, EIGRP only multicasts the updates. When in OSPF down here, hello packets, to find its neighbors, and then we had the link state, the state of the links were broadcast. In OSPF, in a broadcast topology, we had a DR, a designated router, and a BDR, a backup designated router. The significance of these guys are, instead of all of the routers talking to everybody else, they all talk to the designated router, and the designated router then multicasts to all of those that are running the OSPF protocol. We had in it the process ID. The process ID is locally unique, and it's used by the protocol to keep track of the OSPF process. And then we had areas. We kept our routers separate by putting them in areas so that a router only talked to routers in its area. Area 0, backbone area, you have to have at least one of them, and all the other areas, here we go, all the other areas have to connect to it. To connect between areas, we trying to look and see what we got next. To connect between areas, we had to have a NIC, here, I'll get there, on the routers in each of the areas. And then the routes, out of area routes showed up as enter area in the show IP route command. The next thing, I guess, that we talked about here a little bit was the routing protocols, switch virtual interfaces for VLAN routing. What we did was use a layer 3 switch, enabled routing on it, had our VLANs, our VLANs through a trunk port going to it, and we created virtual interfaces, interface VLAN 1, VLAN 2, VLAN whatever else, and then it was able to switch route the packets from one to the others. And I jumped down. I don't know why I didn't have this LSAs in the link states. OSPF2 establishes adjacencies. When we did OSPF, the process ID, and then after that the network, and then the network address, and the wildcard mask, followed by the area that it was on. And LSA's link state announcements was what OSPF uses in order to establish the adjacencies. It sends out an announcement, and if it gets a reply, then it'll attempt to establish an adjacency with the neighbors, and the timers and all of the information in the adjacencies had to be the same in order for them to establish that adjacency. And we talked about areas a little bit earlier. Area is just simply kind of an administrative management that we're going to be able to do things. Okay, Dominic, I appreciate you being here. You can watch these things, and we'll do the other things. I am sorry to hear that. That's very painful. So, link state announcements areas where areas are kind of administrative management functions that the all of the routers with OSPF and Area 0 talk to the Area 0 routers, and the Area 1s to the Area 1s and 2 to 2s and so on. Multi-area OSPF we talked a little bit about, and that's where we had the area border router, and all of the routers have to touch Area 0. The area border router or routers have a NIC in each of the areas so that they get the routes from each of the areas, and then they serve as the I guess as the communication point for those areas. When we send from one area to the other, again, we have inter-area routing that's used there. OSPF v3 was for IPv6. We configure it, let's fix the configure it without the W. Configure it at the interface. We've got to put an R in there, don't we? That's why we had the W. Configure it at the interface, and it needs a 32-bit RID, a 32-bit router ID. EIGRP v6 is also going to need that 32-bit router ID. So each of them needs the 32-bit router ID. When we go to ON, we talked about EIGRP. EIGRP, the Cisco proprietary that I understand has been made available, but nobody is using it. So EIGRP, Enhanced Interior Gateway Routing Protocol, an updated version of the old IGRP. One of the advantages to it was it could be used with multiple routable protocols, IP, IPX, and the other ones that might be available to it. We use an autonomous system number with EIGRP, and much like the areas with OSPF, the routers only share information with other autonomous systems. It had an auto summary capability, which is now off by default. On older ones, it might be on, so you would have to give the no auto summary. What auto summary does down there is summarizes routes on the router as it goes out the interface, summarizes them to the classful boundary, which we may not want to happen. To find the state of the auto summary, we use the show IP protocols, and in there it had auto summarization and hours set off in the little demo that we did, and that would be the default. We have hello messages in order to maintain the neighbor relationship, to be sure that the neighbors are still up, and we had the different basically dead timers. What was it, 3 times the hello time, and then they considered a link down, and I think that was 15 seconds, so 45 seconds for a link to go down. But we also have goodbye messages. When a link goes down or we shut a link goes down, the router sends a goodbye message, and the purpose of that is to tell everybody that the process is locally terminated. It's a locally terminated process, and to expedite convergence of the routing protocol. And more things here. We had in EIGRP, we had a route table and a topology table. We had successor routes, and again, when you see successor, think successful. The successor routes are the ones that are going to go to the route table. Feasible successor routes are backups, and this is the reason that EIGRP is able to converge so quickly, is because it has the routes that are being used in a route table, and the backup routes. And the backup routes are just sitting there waiting. They're not participating in the routing topology at all, but they're in the topology table. So successor and feasible successor routes are in the topology table. Only successor routes are in the route table, and only the routes in the route table are going to be used. We had in the topology table, we had a reported distance and a feasible distance for EIGRP. The reported distance has got to be less than the feasible distance. What the reported distance is what your neighbor tells you the cost is to get to that route. So you take the reported distance and add your costs to it, and then you have the feasible distance. The lowest feasible distance obviously is going to be the successor route because we want the lowest cost, just like if we're going out shopping, we want the lowest cost. Did a little experiment on the external EIGRP routes and redistributed routes. First we did a redistributed route and they became external. And the external routes, we have a EIGRP internal and an administrative distance and an EIGRP external administrative distance. The internal is 90, the administrative distance, and the external administrative distance was 170. And when we redistributed RIP into EIGRP, lo and behold, they became external routes, and they had an administrative distance of 170, which is what we would expect for the external routes. EIGRP v6 was in shutdown mode. If you remember, you had to give it the no shutdown command for the protocol in order to activate it. It was configured on an interface basis, just like OSPF v3, which is the IPv6 version. And we still needed an autonomous system number for these things to share information. By configuring it on the interface was the same as advertising it with a network address, and I think it has an upside and a downside to that. To me, version 4, where you put the network address in, is a pretty straightforward way to do it, but to type all of those, after you get the addresses on the interface, to type all of those 128-bit network addresses is kind of a pain. Cisco Express Forwarding, I think we probably didn't really say a whole lot about, like probably nothing. I think it showed up in one slide and I didn't go into it in detail, so we'll go into it in a two-point slide here. Cisco Express Forwarding is what Cisco uses to make the routing process faster. It has two tables in it. The FIB, the forwarding information base, which is the layer 3 addresses, and the AT, the adjacency table, which is a layer 2, is going to have layer 2 addresses in it. So we have two tables, the forward information base. The adjacency table is just a quicker way to get it. We don't have to go through all of the ARP processing in order to get from there to here. HSRP, hot standby routing protocol. The standby command, we use the standby command to configure this thing. This is where we had the virtual interface. We had physical interfaces where we had IP addresses, and then we configured them to be part of a standby group. And the standby group had its own IP address, and that's the one that we're going to use in our network, in our DHCP, for the default gateway, because this is for a first hop redundancy protocol. It's designed for our default gateways. Show standby was our primary troubleshooting command. Show standby showed us a lot of information. The groups, which is the active router, and the priorities that were on it, whether preempt was enabled, all sorts of things were there. And in it we had one active and one standby router. We did that little demo on GNS3, and when we put a third router in, it goes into listen mode. The active router goes down, the standby router came up, and the listen router then became the standby router. Those were all the same priority, so it was based on the IP address, which one would get elected as the active router. An election process, we can dictate what priorities we want to use, or we can leave it alone and let it all be the same, and then it's going to use the highest IP address. In order to do that, you probably are going to want to tell the system which one we want to be, and we did that by assigning a priority above the 100, which is the default on the one on down there a little bit, and preempt is not the default on HSRP, and we talked about the virtual router a little bit already. So on it we have one active, one backup, and all the others that are configured as a part of the HSRP group are going to be in listen mode. And then down there, the highest priority is the one that's going to be the active one. Uh-huh. Well, here they all share one IP address. They both use the virtual router concept. Let me let me go through and do a bad sketch, okay? No, 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 no. This is the time to ask those questions. We have these two routers here for HSRP, and then we have our, we'll call it our VR here, our virtual router, and our virtual router is going to have the IP address that we're going to use, and we'll say 192.168.1.1 because we normally use the one address for the default gateway. The NICs that are part of the group, that are part of the HSRP or VRRP group, are going to have addresses 192.168.1.2 and .1.3 maybe. We go into the interface, we have these addresses on them, and then we use the standby command, standby, and then whatever the group is, standby 1, and then we give it the address that we want the virtual router to have. And then we use standby, and if we want to change the priority, and then if we want it to have a preempt capability, we would give it the preempt command. From a virtual router standpoint, VRRP does the same thing. It can have more backups. Each of the other routers that get added to it become standby, I think. No, they become backups. One active, and I say backup here, this actually should be a standby, right? And we had active, and we had backups at VRRP, but the virtual router thing is the same. They both use a single IP address, and it's a failover that really doesn't affect the traffic. This router goes down, this IP address automatically fails over to this router. When this one comes back up, if it has a higher priority and we've configured preempt, it will automatically assume the active role. VRRP preempt is the default. Does that make sense to everybody? Some sense? Any sense? Hopefully sense. They show standby. They do them on the election. You can force some of this stuff with priorities, because if we did a priority 140, 130, 120, 110, then they're going to have that particular priority with and standby. Had configure standby in HSRP. VRRP, basically the same process, same priorities. Priority of 100 is the default. You can have multiple backup routers in it. Each of the ones that's not active is going to be a backup. Whereas in HSRP, we're not going to have one. The others are going to be in listen mode. VRRP, the preempt is default, whereas we have to configure it in HSRP. They're very, very similar protocols, as hopefully you see. And then we talked about cloud services, software as a service, platform as a service, infrastructure as a service, and I think that there wasn't anything really magic about those. You guys have used virtual whatevers we're using with software as a service is what we're doing right now with Zoom in order to do these classes. access control list, again, standard and extended, and I think this portion of it focuses on the extended access control list, the troubleshooting. Be sure that you check it before you add the access control list to the interface, because if it didn't work before, it's not going to work after. The extended allows us to use the source destination address as well as TCP UDP port services, so that we can be very precise on what we allow or disallow in the system. VRRP, Virtual Redundancy Routing Protocol, was a standard. We've discussed that a little bit earlier. It had a master and a backup. We could have multiple backups, and the terms, what do we have? The active and what was it? Active and standby is what I thought. Active and standby routers, or master and backup, the terms that we use. Quality of service allowed us to assign priorities for traffic. We marked the traffic, classified the traffic, created a policy. Policies where we use the marked traffic, that's what it's supposed to be. First we define what traffic that we want, and there were a number of ways to do that. We used the access control list, which was the access group, just like you would apply it to an interface. Then we classified the traffic based on what we had decided that we wanted to do. The class policy used the access control list to classify the traffic. Then a policy where we applied what we wanted to do with that traffic. In the case that we did in the demo, we set it to a precedence of 5. So we marked that traffic, and the access control list was the one IP address. And then the service policy applies the policy at the interface, and it could be inbound or outbound. We talked about congestion management and congestion avoidance. Congestion management was where we dropped packets, basically, and congestion avoidance was where we took actions prior to the congestion in order to prevent it from happening. The things that we were looking at in the quality of service were latency, jitter, bandwidth, and packet loss. Latency is the delay. Jitter is a consistent, or jitter is inconsistent delay, and that can cause issues with voice and video, as some of you have configured. We have bandwidth and packet loss here. Cisco device, the trust is off by default. We have to tell it to do that. And then we talked about policing and shaping. Policing was where you just dropped the packet at a little image that in a voice that it looked at the policy, and if it exceeded the limits, then it dropped the packet. Shaping basically buffers the data, the information, the whatever it is, and when we go below the limit, it then sends whatever is buffered. So it helps it a little bit. Something that we looked at a little bit was the IPv6 flow label, and it was something that was used to mark a series of packets as a flow, as part of a flow, so that they didn't get broken up. So SNMP, and this was the actually attack action radius was the last one, but we had the managers and the agents to do that. The manager was on a workstation. I talked about PRTG and MRTG as a couple of managements, places where we report that the devices report their status. And then we had the SNMP agent, which was on the device itself, on the router or the switch. We had get and set messages that we could either get information, and then we used the set messages in order to change the characteristics of the devices itself, to modify the settings on them. Read-only, read-write communities in SNMP version 1 and version 2. We had community string, which we'll go back to areas and autonomous system numbers. The community string, which is a text string, all of those that are a member of the community share their information within the community. So we had read-only and read-write. Read-only, we can only monitor. Read-write, we can actually make changes to it. Read-write, you need to be sure that you have set something up, and that's where SNMP3 comes in because it has security. We had integrity to be sure that something hadn't changed, the hash, authentication, and encryption, and we had 3 levels of SNMP that we could set. And the reason is that the more security that you add to anything, the more processing power it's going to take. And the MIB was the information base, management information base that we used in the on the SNMP agent. And each of the devices, each of the endpoints that we, or things that we were measuring, had to have a MIB number, which was a series of numbers that we looked at. Lesson 8 was TACACS and Radius. TACACS used TCP, Radius used UDP, authentication, authorization, and accounting. We can do accounting on the 2 servers here. Local, if we use a local authentication, there was no accounting available in it. In order to get to this, we use the AAA new model command. After that, we would then define the authentication methods using the methods list that we want to use for authentication, authorization, and then we could configure accounting to store the basically the start stop of the sessions or whatever we were monitoring on our AAA server, either TACACS or Radius. Local is no accounting in the method list. AAA accounting default might have group Radius, local enable, and then maybe none, that if we got down to the end that we could still configure our information. The methods list was one that if a method failed, then we would be able to go to the next one. If we just didn't know the password, we're trying to hack it, or didn't know the password, forgot our password or whatever, and we timed ourselves out, it doesn't go to the next method. It stays there. The method is not, oh yeah, I forgot how to do it. The method is for, I can't communicate with the Radius server. So, are there